first property that we'll see is what is called as the causality. So what we mean by a causal system is something where the output at time t depends only on the input at time t or earlier, which means the output at present time depends only on the past and the present input and nothing else. So this is what we mean by causal. So what does it mean? So we know that this output is caused by only those that are in the past, hence the term causal. So anything that is caused only by the inputs which were present earlier or at the current time is what we call as causal. But what if there are systems which have output that depends upon the future? Okay, then we say that okay, this system gives an output whose current output depends on future inputs. Then we say that it is non-causal, which means the current output is caused by inputs which are not even seen yet. So such kind of systems are non-causal. Of course, you know that there is no system which you can construct whose output would depend upon the future, right, in reality. So all practical systems are causal. Then what is the point of studying even non-causal systems? So it will so turn out that when you mathematically model systems and then try to optimize certain parameters. Now let's say I have mathematically modeled some system and then I want to optimize some parameters. I want to find out the best capacitor, best resistor that I can put in so that I'll get the best possible filtered output. What if it so turns out that equation gives you a number which corresponds to a non-causal system? So that means you will end up getting a solution which is not implementable in real life. So in order to know this, you need to know what are non-causal systems and how they are modeled. So whenever you solve such optimization problems later in your design of electronic circuits, you'll have to add this constraint and then say that, okay, I want a solution which is optimal, but not only just optimal, but also causal. Only then you can actually implement it. There can be solutions, there can be a set of values which you can get as a solution as the optimal solution for a particular design problem, but it can be non-causal. In fact, that will be the case for several filters. The optimal filters that you can design will end up being non-causal. So in real life, what we'll do is in order to implement them, we'll have to somehow make them causal. So we'll have to adjust the parameters in certain way so that the system ends up being a causal system when you implement. Hence, the study of non-causality is very crucial so that you know that your design is implementable in real life. You can just solve some set of equations and then say these are optimal values and then say that this is the best possible design. But there is no point in giving such a design if it is not implementable. So you need to know causality. So let's see some examples of causality. So if the output of a particular system is given by just scaling the input with 0.3, is this causal? Yes, it is causal, because all it is doing is taking the current input, just scaling it with 0.3, the amplitude just scaled. This is an amplifier. So this is a causal system. Now let's see the next system. The output at time t is nothing but the average of the input at time t and t minus 1. What does this mean? It means that if I want to see what is the output at t equal to 1 second, then you take the input at t equal to 1 second and the input at t equal to 0 second and then average them out. So the output at t equal to 1 second depends upon the input at t equal to 1 second and t equal to 0 second, which is the past. So the output always depends upon the present and the past. So this is still causal. You can still implement it. Okay. All right. Now let's see the next one. Now this is a weird system where it says the output at t equal to 1 second is equal to the average of the input at t equal to 1 second and t equal to 2 seconds, which means the output at 1 second depends upon the future. And this is the case for every time instant. Any time instant you take, it is the average of the input present at that time instant plus whatever would be the input at the next time instant. You don't even know what would probably be the input the next time instant at this current time instant, right? So which means that this is dependent upon the future. So this is non-causal. What about this case? So y of t is x of minus t. So basically what we are trying to do is we are doing time reversal here. So what is the output at 1 second? The output at 1 second is minus 1 second, which is dependent upon the past. That is okay. Output at 2 second, 1 second dependent upon the past, minus 2 seconds. This all seems fine for the right side or the positive values of time. But what if you try to compute the output at t is equal to minus 1 second? Then it depends upon the input at t equal to 1 second, which means for negative values of time, the output starts depending upon the future values, which makes this system essentially non-causal. Okay. So one part of the system here is causal, the other part is non-causal. Even if there is one particular sample of the output which is non-causal, we say that the entire system is non-causal. Okay. So this is a non-causal system. All right. What about this system? Y of t is equal to x of t plus t. Basically, the output is a time shifted version. So if t is negative, then we have a right shift. If t is positive, then we have a left shift. Okay. Now, so which is causal? So if there is a delay, then it means that it is still causal, which means that the output at t is equal to 1 second corresponds to the input at t is equal to 1 plus capital T seconds. So if let's say t was negative, there are two cases, t is negative. In this case, the output at 0 second depends upon the output at minus t, and the output at 1 second depends on 1 minus t, and so on. The output at minus 1 seconds depend on minus 1 minus t seconds. So in this case, whenever t is negative, capital T is negative, then you see that the output is always a delayed version of the input, right? It is just only a right shift, which means that it is a delayed version of the original signal. So if x of t looked like a rectangular function, right, then y of t in this case is just a right shifted version, which means whatever was at 0 now will come at, let's say, some capital T, right? So there is a delay. Whatever was the input that was fed at 0 second now appears only at capital T seconds, after capital T seconds. Whatever was at minus 1 appears at minus 1 plus capital T seconds. There is a delay of capital T seconds here. So this is still causal because the output depends on the past. So when capital T is negative, you have a causal system. Now what if capital T was positive? So in that case, then the output would be a left shifted version of the input. Okay, so whatever was the input at 0 seconds now is appearing at minus 2 seconds, which means the output at minus 2 seconds depends upon the future value, that whatever that would appear after 2 seconds is what now I am saying as my current output, which is like I am going to predict the future. So predicting the future is first of all not possible in reality. So this is a non-causal system. Okay. Now let's see this case where the output is shifted in time compared to the input. So earlier the input was shifted in time. So here the output is shifted in time. So what does this mean? So this means, let's first take the case when t is negative. So which means, let's say capital T is negative. So at small t equals 0 seconds, we get the output at capital T depends on x of 0. Once again, this means that this is non-causal. Why does this mean that this is non-causal? Because let's say capital T is minus 2. Then the output at minus 2 seconds starts depending upon the input at 0 seconds, right? Which does not define a causal system. A causal system has to have input only that depends upon the past or the present. So this makes this system to be non-causal. On the other hand, if t was positive, then we'll say that let's say capital T, for example, is +1. Then at small t equals 0 seconds, the output is y of 1 second, which is the output at 1 second, will start depending upon the input at 0 seconds, right? Which means that this is depending only on the past, and hence this is a causal setup. So as you can see here, it is possible that depending upon the time shift, which is either done in the output or in the input, can make the system causal or non-causal. So there are two things that you have to check. What is the sign of this time shift? Is it shifting to the left or the right? And where is this shift happening, at the input or the output? So that can make the system causal or non-causal. So also we saw our standard systems, right? We also saw this integrator, differentiator, time shifter and amplifier. Are these systems causal? So let's first talk about the integrator. Okay. So the integrator, is that causal? Of course it is causal, because all it is trying to do is compute the area till the current point. So if I'm trying to find the output of an integrator, it is the area of the signal that was fed as the input from minus infinity, basically all the past, till the point of current time. So which means it depends only on the past and present, hence this is causal. Now what about differentiator? Of course it is trying to compute the slope at a particular point, which depends only on the current point and the immediately previous point. It takes these 2 points and finds the slope between them, and hence the derivative is also a causal system. Okay. And time shifter, we already just saw what is the causality of a time shifter system. It can be causal or non-causal depending upon how you are shifting. So the other one is amplifier, and we already saw amplifier also. The first one that we saw here is basically an amplifier, so that is also causal. So the standard systems, of course they are causal because they are real life systems. They have to be causal. If you have any system which is implementable in real life, they are necessarily causal. So if it so turns out that you have to implement a non-causal system, that you have designed a circuit and it so happens that I have to implement it no matter what, there is no other option, then one way to implement non-causal system is to introduce a delay, which means that you will say that, okay, I'll wait till all my future inputs arrive, I'll store them in some kind of a memory and then process and then give the output. So introducing a delay in the output is one way of creating a non-causal system. So an implementation of a non-causal system can be done in practice by introducing a delay. So the moment you introduce a delay, it automatically makes it a causal system, but it is one workaround to have a non-causal system.